ease with which this short length of high-grade red rubber tubing can be twisted shows its flexibility and resiliency. Let's bend it again and place the folded section in a glass tumbler. From a vacuum container, we'll pour in some liquid air. Liquid air, you know, is ordinary air which has been compressed and cooled until reduced to a liquid. Because liquid air is so cold, some 310 degrees below 0 Fahrenheit, other materials in comparison are hot. This difference in temperature accounts for the boiling and steaming. But what is happening to our length of tubing? It has been contracted and frozen so that it's hard and brittle. When struck, it shatters into chips like rock candy. This time, we'll experiment with some mercury, which freezes around 38 degrees below 0, a high temperature in contrast to that of liquid air. Then into the two liquids we'll insert a pencil and pause a few moments while the coldness of the liquid air reduces the heat of the mercury below its freezing point. Now it is a solid. The glass can be cracked off and we have a small hammer. It will stay a solid for only a moment, reverting to its liquid state as it warms up. Here's a practical use for this super cold. The outside diameter of the shaft is 1/1000th of an inch greater than the inside diameter of the rings. A force fit between the shaft and the rings is desired. So liquid air is used to contract the steel shaft, to shrink it temporarily so the rings may be slipped on. This application is exemplary of the search continually being carried on by science and engineering for new ways of doing things or ways of doing new things. The usual method for assembling such parts is to heat the rings, thereby expanding them until they can be slipped on the shaft. This heating, however, sometimes has a bad effect on the metal, lessens its temper. It is also a costly procedure, hence the need by industry for a new way of doing this job. Now we'll remove the shaft with a pair of tongs, for the liquid air is too cold to touch, even with the asbestos mittens. Slide an arbor with the one of the rings on it into place and insert the shaft. That the shaft has been temporarily shrunken is evident from the ease with which the rings are now slipped on. The assembly is then allowed to warm up to room temperature. The frost shows that the shaft is expanding to its normal size. And now to see how securely the rings fit. Thanks to liquid air, they are tightly affixed without injury to the metal and at little cost. The final step in the manufacture of many products is the application of a varnish, paint, or enamel coating. Since this coating not only protects the metal from corrosion, but also makes for an attractive appearance, it must be durable. Durability, however, depends upon many factors, one of which is the thickness of the coating applied. Too much is sheer waste, too little is false economy. But how can one measure the thickness of such a coating when only one surface is exposed? Thin materials are usually measured with a micrometer, a metal gauge which gives a measurement, however, from both surfaces. This non-magnetic material, a square of colored celluloid, is 31.5 thousandths thick. By laying the same material upon a sheet of steel, we can now measure its thickness, though only one surface is exposed, with this electric gauge. The thickness, as indicated by the pointer on the scale, is the same, 31.5 thousandths. As you can see, there are two parts, a small indicating unit and a half-pound gauge head connected to the unit by a cable. Within the head is a coil of wire, which, when electricity is passed through it, magnetizes a soft iron core in the center. This core and the outer metal ring thus become magnetic poles. Just to show the presence of this magnetism, we'll pick up some ordinary pins with the head. Now let's measure the thickness of some sample coatings of enamel which have been sprayed on steel sheets. The pointer indicates the thickness directly in thousandths of an inch. Because this instrument permits quick and convenient measurements of the thickness of paint, enamel, varnish, or other non-magnetic materials which have been applied to or laid on sheets of steel, the thickness of such materials can be readily controlled. Such control not only saves material, but also makes for a more uniform and durable product. With this device, called a cathode ray oscillograph, it is possible to see sound, to picture sound as we hear it. When the switch is turned on, a narrow band of light appears. As we make adjustments, however, we find that this light is not really a line, but just a little dot in a great big hurry. As we readjust the control circuit, the little dot travels faster and faster until, as it crosses about 120 times each second, our eyes deceive us into seeing a line. By playing a single sustained note, we can make the little dot go up and down also. By playing a note an octave higher, we can see twice as many sound waves. But now, just for fun, let's watch the little dot picture the sound of Old Black Joe as played by the well-known banjolier. By the proper application of these oscillographs, it is possible to check radio receiving sets so that one may be sure the program he hears is being faithfully reproduced.